Welcome to the pre-recording of lecture 28 of MCS 481. So today we will analyze the cost of an incremental randomized algorithm or a randomized incremental algorithm to compute Delaunay triangulations. So I will start by trying to make this lecture as self-contained as possible, but we are in the middle of week 10 of the semester. In a way, this lecture is a really nice lecture because a lot of things are coming together. On the other side, it's a very complicated lecture because we are using a lot of ideas and concepts we have been practicing throughout this course. Okay, so what is a Delaunay triangulation? A Delaunay triangulation maximizes the minimal angle over all possible triangulations of a point set. So in a way, this definition looks very complicated. Um, However, the complexity of a triangulation is linear in the number of points. So we have a number of triangles proportional to 2 times n and a number of edges that is proportional to 3 times n. In a triangulation, we are using all our points in the input. So that is important as well. This is different from the convex hull problem we started with. So that's why we have this factor k that occurs here in the complexity. So in some sense, the definition is kind of daunting um, over all possible triangulations. On the other hand, the complexity, uh, the way we, the amount of data that we need to store a Delaunay triangulation is very encouraging. And it includes the possibility for an n log n algorithm. All right, how do we make better triangulations? Well, we look at the circle that passes through 3 points. This is called the circumcircle. Then for an adjacent triangle, we say that the edge that is shared between these 2 triangles is legal if the point, the other point in the adjacent triangle, so here the point S, if that point lies outside the circle. If it lies inside the circle, then it is illegal because we can obtain a better triangulation by flipping the edge PQ by the edge RS. So this is the application of the circle theorem of Thales that we have covered in an earlier lecture. So this arises then, so geometrically we have this characterization that a triangulation of a point set is Delaunay, is this angle optimizing if the circumcircle of any triangle does not contain any point in its interior. Okay, this is geometry. Let's look to some algebra. So if we have 4 points, not all on the same line, then we can define affine dependencies between the coordinates. So an affine dependency is a non-trivial linear combination of these points. So non-trivial, you can have all the coefficients lambda equals 0, but that's trivial, so that's not allowed. So it is an affine dependency unique up to a non-zero multiple. If you have such affine dependency, then you can look at the plus signs and the minus signs in these coefficients. And there are 2 possible triangulations of such a set of 4 points. One triangulation T plus consists of all the triangles that you can, so you have the set of all the plus points and the minus points, the points with the plus coefficients and the points with the negative coefficients. You consider all the points and you remove once a plus coefficient, once another plus coefficients. That gives you the T plus. With the T minus, you do the opposite. Um, the point of the exercise is to verify this for the unit square. And you can read off what the coefficients could be. So the coefficients are up to a non-zero multiple. So I can pick 1 for lambda q, 1 for lambda r. Q is 1, 0, r is 0, 1. Then if I want to make 0, I have to set lambda s minus 1. So I have 1, 1, minus 1. So that gives me 0. And I have still freedom for lambda p. So I have that the sum of the coefficients must be 0. Reading from right to left, I have minus 1, plus 1, plus 1. So I have plus 1. So lambda p has to be minus 1. Make a drawing and verify that indeed you have these true triangulations of the unit square. And that is one way to compute algebraically the edge flips. So by computing an affine dependency among the points and looking at the signs of the coefficients. So these affine dependencies are called circuits. So they appear very prominently in matroids. This is just a side way. Okay, so on the other end, so we have many software systems. So Delaunay triangulations are very important for many industrial and geometrical engineering applications. Think about geometric modeling. So throughout this course, our prime software is the computational geometry um, algorithms library. The Voronoi diagrams and the Delaunay triangulations are both wrapped in Python. What I do here in this lecture, so in previous lectures, we were focusing on the um, Python bindings. Also, SciPy provides it. Um, Here we look at the C++ code. So I'm running this on a Windows subsystem for Linux. I have installed Seagull with the, so it's nicely wrapped. The examples have been downloaded separately. And it's kind of strange. I have selected the Voronoi from the examples in the triangulation underscore 2, which seems awkward. But we will be relying very heavily on duality. Duality was introduced in the last lecture. I will try to make it self-contained. But here you see the source code. So you see that indeed we are making a Delaunay triangulation. So we are inserting the points in this triangulation, and from the output of the Delaunay triangulation, we can count the number of edges and rays in our Voronoi diagram. So you see there is the dual that is actually built in. So the source code is quite small. So what I do is I copy the Voronoi in my folder. So this folder where I'm currently in has our examples that we have tested so far, or that I have tested during the course. So I like to work with my own make files. So here you see, since everything is properly installed, I can use the system G++ and then run the code. So here we compute essentially a Voronoi, so we compute the characteristics of a Voronoi diagram of a point set via the Delaunay triangulation. When we get to three-dimensional convex hulls, we will be able to explain the construction that is used in SciPy to construct the Delaunay triangulations. Okay, that is the introduction. Oops, why did I just do this? Let's now look into a self-contained algorithm to construct the Delaunay triangulation. Why is that important? Because we have seen that the complexity is linear in the number of points. So we can come up with specialized data structures. And that is also what Seagull contains as well. All right, here is the outline of our randomized incremental algorithm. So we are starting from, it's incremental, so we are starting from the highest point. Um, if there are two, we actually do the rightmost highest point, but I will indicate how we can do it a little bit better than what is outlined here. So we have an initial triangle, and then we run over all the points. We locate the triangle that contains the next point, and then we update. So our first triangle is large enough to contain all points, all given points. So we add two more points, p minus 1 and p minus 2, so that we have this property. Now there is a random permutation of the input points minus the highest point. And why do we do this? So that makes the algorithm randomized. We've seen that we can do a randomized, we can compute a random permutation in time linear in the number of points. So that is a step that is easily absorbed in the entire computation. Why do we need to do this? Well, look at how the point location goes. So in the point location, we will have a graph. So here I'm looks like I'm having in on the example I have two triangles and looks like I have a binary tree. But you could also interpret this that you have essentially a forest of trees where we start at the triangles um, delta 1 and delta 2. Or the root is actually the information stored from the initial big triangle. So the point is what happens when you add a point. So if the point is the next point is this point here in the middle of the first triangle, then we replace the first triangle by three new triangles. So the inner nodes in this directed acyclic graph actually store the triangles that are no longer there, kind of the ghost triangles, but they are used in the point location. So this is adding one point, but as you perhaps already can see, if you have followed carefully the discussions on angle optimal triangulations, then you see there are some very sharp angles between these two adjacent triangles, delta 2 and delta 5. So the adding of the point is actually not yet the entire update. So there is a next step. So we must replace the illegal edge that is shared between delta 2 and delta 5. So it's a directed acyclic graph. So we store in the leaves the triangles and we store the leaves only once. So in a way, you can get to delta 6 via the old triangles delta 1 and delta 2. So delta 6 has a part that is shared between these two initial triangles. Okay, so this is not a programming exercise, but it could be a good exercise here to think about how you would store and how you would work with this directed acyclic graph. For us, it's very important that the number of checks that we have to do to locate a point depends on the depth of this directed acyclic graph. If this depth is going to be linear in the number of points, then the point location will be linear. And we have already an outside loop. So for every point that we add, we do a point location. If the point location is linear in the number of points we have already, we have a quadratic cost algorithm. And this depends on the order of points. So in some sense, you can't really avoid this. Okay, so the second exercise is again an algebraic excursion. So if there's too much geometry for you, and also it invites you essentially to think about the um, the tests of in the point location. So when does a point belong to the inside of a triangle? Well, if you can write the point as a convex combination of the vertices of the triangle. So you solve a simple 2 by 2 linear system for this. So here, this arrives at barycentric coordinates. So you want a convex combination. You can always solve this system. So there are three equations, three unknowns, and we are assuming that uh, the points do not lie on the same line. So there is a unique solution for this. Then actually, if you look at the signs of the coefficients, if they're all possible, or if they're all positive, then you will be in the interior. But if you have also the cases where there are negative coefficients, then they will actually tell you which point you have to swap out and go to an adjacent triangle. So by this computation, you can actually figure out on which side a point lies if it's not inside the triangle. The triangle have three sides, three edges, which edge you have to cross to get into the triangle that is adjacent to this triangle. This helps in the navigation. Um, so that's the point of this exercise. Okay, so why randomize here? So I was trying to indicate this. Here it is written now. So if you follow my narrative, then the what is written here is confirming this. We randomize because we know that the very unlucky orders in which you always replace the last added triangle, if you do that, then indeed the graph will become deeper and deeper in every step, in every point that you add. If you do that, you have to be extremely unlucky. So the point of exercise 3 is more geared towards building such an analysis. So it is so the cost that then actually risks to become quadratic. Now, if you are a data structures person, you know about self-balancing search trees. So there is a way to get around this, and in some sense, with the exercise tree, if you do it very systematically, work with 1,000,000 points, for example, then quadratic cost is really very expensive. If you are systematically figuring out a sequence of points such that the last point always lies in the uh, convex hull of the previous 3 points, then actually you can build a challenge, a potentially challenging um, sequence for um, any construction of a Delaunay triangulation for an incremental way. Um, and it may be that there is some randomization, but I don't think so. So we also saw in the Python interface that we insert the points one after the other. Um, so this exercise, it can take a lot of time if you do it, but it could also lead to some very other interesting properties here. Um, we are mainly interested in our cost analysis in the average. What we don't really say is what we're not going to investigate are the standard deviations. So it can be that you have a very nice average, but that the standard deviation is kind of large. So if you so an alternative, if you are more a brute force person and if you have a lot of computing power available to you, you could take 1,000,000 points and run all possible combinations. Actually, you can't do this. 1,000,000 factorial might be a little bit too excessive, but you could do many, many runs and check on the fluctuations of the running times. You will see that they should actually be n log n. So that's actually a topic for the next computer project. Okay. Um, I'm almost halfway, and let me say what happens when you have two highest points. So instead of having an initial triangle, you could uh, do it differently. So you could consider somehow a sandwich construction where you have two half lines. So one half line at the top starts at the vertex p minus 1 and goes all the way to infinity. And the other half line runs from, or the other ray runs from p negative 2 to infinity, to plus infinity at the other side. So we have the highest and the lowest point. We don't really need to worry now again whether this is the rightmost or the leftmost. What we will do is we will consider these two vertices, p minus 1 and p minus 2. So that is to replace the initial triangle, and we can even deal with these points symbolically. So we started the scores with the left hull and the right hull, or actually the lower hull and the upper hull. So you could play this game also, instead of, if you don't like horizontal sandwiches, you can do vertical sandwiches. Um, but in any case, the idea remains the same. So every point here at the left makes an edge with the p negative 2, and every point on the right makes an edge with p negative 1. Again, the convex hull may confuse you because we need the vertex set is the set of all input points. So we won't throw away any of the points because we have geometric modeling um, as an application in mind. All right. I'm sorry, so I'm contradicting myself. Actually, we do have the convex hulls that we are constructing. That's the initial construction here. Um, this is n log n. Um, so you can initialize your Delaunay triangulation like this with the convex hull. This is also where the k comes from the complexity. So these are the points on the boundary of the convex hull. All right, I'm halfway, so let's now start with the effective analysis of the costs. So let's start with the storage cost. We do have the directed acyclic graph, and the directed acyclic graph stores every triangle only once. So it's not a tree, although we can treat it a little bit like a tree, but we store every triangle only once, and the number of triangles is linear in the size of the input. So that's the first complexity theorem that is applied here. So we have proven that first complexity theorem in an earlier lecture. So the second point, the size of our triangulation is also linear. Okay, that was good. Now comes the harder part. We know that the worst case scenario, we could have a quadratic time algorithm. However, if we are computing, so the average number of triangles that are being computed is linear, and actually we have a sharp bound 9n plus 1. Okay, what will we do? We will consider the next point, and we will focus on one point. What is the number of new triangles added by the next point? And we will count the number of new triangles. And we will average this over the R points, where R is the current point, the index of the current point that we are considering. So we will compute averages. That's the meaning of this theorem. On average, in some sense, I said a sharp upper bound. That's not actually right. So we have a precise average. And the most important thing is that it remains linear. Okay, the 9 is indicating that there is a good reasoning to get to that linear bound. Okay, I will be using the dual. So in some sense, that's also the reason why I picked the Voronoi, the C++ program that says something about the Voronoi diagram via Delaunay triangulation. Here is the construction for a very regular collection of sites. We have 8 points with 1 point in the center, so we actually have 9 points. We have a regular octagon in the Voronoi diagram. At the right, you see in red the edges that are being added. So in constructing the dual, with every Voronoi cell contains a vertex, so that's the original site. If two Voronoi cells are adjacent, we draw an edge between the vertices, between the sites in the original Voronoi diagram. So we see the Delaunay triangulation as a dual graph of the point set of sites. So why is this important? Well, we have studied Voronoi diagrams for one entire week. So in some sense, the Delaunay triangulations and triangulations in general are extremely important. But if we understand Voronoi diagrams, the properties of Voronoi diagrams, we also understand a lot about the Delaunay triangulations. This example, by the way, was used to illustrate that the complexity of one single Voronoi cell could be linear in the number of points. So we have 9 points and the middle cell has 8 edges. But then as an exercise, I was asking about the number of average edges in a Voronoi cell. We will solve this. So that was left as an exercise. In some sense, we will solve this exercise here via the Delaunay triangulations. So if this exercise has been troubling you all along, we will solve it here. So properties about Voronoi diagrams you can derive from the Delaunay and also the other way around. Okay, let's count the number of new triangles. We have seen, and perhaps I should draw another picture here. So we have seen that if we are locating a point, so we have a triangle, oops, and we have a new point that sits inside, then actually we're going to add 3 new triangles. That is actually why 3 uh, is the number that we will be using. So we reason about the Delaunay graph. So in some sense that graph is planar, but it's not necessarily a triangulation. So it's good to keep that in mind a little bit. So the number of new triangles depends on the degree of a vertex. So we will denote this here by K, that degree of a vertex. In general, we do have 3, but we may have more new triangles that we are adding. So, and that depends on the degree of the vertex. So, but 3 is here actually the important number. Okay, let's now count the edges. So, what is now the expected degree? So we think about the Delaunay graph. So here is the definition of the Delaunay graph again. It's the dual in the sense that we keep the vertices of the point set of the sides, so they're just copied. And then we are connecting these vertices in the graph if for 2 adjacent Voronoi cells. Okay, so how many edges do we have? So the number of edges of the Delaunay graph equals the number of edges of a Voronoi diagram, plus 3, because we have this initial triangle. So if we know the edges of a Voronoi diagram, then actually we know the edges in the Delaunay graph, plus 3. Okay, so from the complexity of a Voronoi diagram, we had actually this formula. Number of points is 3 plus r plus 3, so 3 times n minus 6. You can check it with lecture 20 or you can check the textbook. We have to subtract the edges from this large initial triangle. Okay, this gives us a formula. So we copy it here and we can simplify this as 3 times r. So if we sum over all the degrees of the vertices, so and counting all the edges twice. So actually what we have is that we do have the sum of the number of edges. So I'm sorry. So the number of vertices are we're counting now. Every edge has two vertices. So the sum is 6r. So if we are taking averages, we are dividing by 6. So that's why we have 6 as the average number of edges in the Delaunay graph. Also, that's the average number of edges in a for one Voronoi cell in the Voronoi diagram. So this is the solution of this exercise. Okay, so we have the formula for the number of new triangles. Um, so that's the bound that we uh, computed earlier. We have the expected number of edges. So based on this expected degree, so we are there are some calculations errors here. 13 minus 3 is 10, so this should be a 12 here. So there's still a typo, so there should be 2. Okay, but the important thing is that we arrive at our number 9. So the expected number of new triangles is 9 when we add the new point. And that proves our first lemma. So this does one part of the cost. If we add a new point, then the new triangles that are computed are linear in the number of points we have already. Okay, so but that's not it yet. So we have to be careful with the point location. So how many triangles do we actually visit? So um, also we also have to take into account it's not only the new triangles that we compute, but we also destroy triangles. So the title of the slide is the expected running time of the point location. So we have a notation, this capital K, uh, that is the set of points that is contained in the circle of any triangle of in a triangulation. So why is that important? Well, what is the chance that we are going to hit a triangle? Well, if the point, if when do we have to consider, say, a triangle? Well, we have to consider the triangle in our point location if that point lies in the circle through the three vertices of the triangle. So con that will be the triangle that we will visit in the point location. Okay, so then the total time of the point location depends on the number of triangles that we have, and it depends on the number of points that are in these circles. Okay, so the sum runs over all new triangles computed by the algorithm. Okay, we will prove a lemma. So if we can prove that the sum over all the point counts of all the points that are in this circle, if that is n log n, then actually this other n doesn't really matter, of the number of triangles, then actually we have an n log n algorithm. So, and that then proves the main result, that we can construct a Delaunay triangulation in a time that is proportional to the time that it takes to sort a number of points. So in some sense, you could see this entire course a little bit as extending the n log n sorts to two-dimensional data structures. Sometimes we call it the Voronoi diagram, sometimes we call it the Delaunay triangulation, etc. Okay, so let's try to prove the lemma. So I will try to do my best to make it as clear as possible, although the notation becomes a little bit involved. So let's see what we're looking at. We're looking at the set of all points that will be visited. Um, we sum this over all triangles. So here is what we are trying to sum. We think of the Delaunay graph. So in some sense, the Delaunay graph can be identified by the Delaunay triangulation. Think of a point set in general position. So we are having our incremental construction. We are considering the points one after the other. R is the index of the points. And then the number of new triangles is the difference between the triangles in the art step minus in the previous step. We can also reformulate this by using this notation with a little k that involves the points, all the other points in the set. So these are the n minus r points, where we are counting the number of triangles in the current triangulation that are visited and that are adjacent to the current, to those triangles, to the visited triangles. So the notation is perhaps a little bit involved, but it is very precise. So when we are constructing new triangles, we not only have to consider the new triangles, but also the adjacent ones, because we may have illegal edges. So that is why these other points Q actually still come in here. Even though it's kind of strange because we haven't considered them yet. So we are kind of also actually doing a backward analysis. Um, I will come back to that a little bit later. All right, so this is the notation. In some sense, it's a little bit unfortunate again that I'm working with slides. Perhaps I can go to a multi-slide presentation again. But let's first see if this is necessary. Let's look at the probability that um, any triangle is incident to a random point in that is any point is just as likely. So we do have three vertices. So the probability that the triangle contains any point is three vertices and 1 over r if we take the average. Then we can, yes, so now I do need the previous slide because we may have forgotten already where we are. And you can see that here we are very close to the end in some sense of this lecture. So we have this notation with the little k. So these are the number of triangulations that are where the number of points that we actually count the triangles that visit Q, um, for which Q is being visited. Notice that Q is a point in the P minus PR. So we take averages, so we have n minus r points. So we may as well take the next point in the sequence. Um, so if I go back to the original single page, so you see here this expectation is having the count of the set P minus PR, so 1 over n minus r. So this is the expectation. So we're going to now eliminate this term here um, so this entire sum actually, so this entire sum appears over here. So we can write one expectation with the big K as another expectation with the little k's. It's just a game of notations, but what will become clear in some sense is that we have simplified the problem. Okay, so we are interested in the expectations and the averages of the number of visited triangles. Okay, so the number of triangles that are visited, so the number of new triangles, is thus bounded by this n minus r over r. And so I have the n minus r that is over here, and I'm combining the 3 over r. So that's how I get the 3 times n minus r over r. And then I have the expected values of the next point here with the little case. So this depends on the difference of the count, and this depends on the number of triangles that are actually disappearing. So let's count the number of destroyed triangles. This follows from the complexity theorem. Okay, so what does this mean? It means that we have the next bound where actually we are replacing this here by the tr minus tr plus 1 minus tr. So it looks kind of, it goes probably too fast, but you see the minus 2 that is coming in, and the minus 2, so it now depends on the number, the average number of edges. So the 6 that is coming in, the average number of edges in a Voronoi cell, the 6, and also the average number in the Delaunay graph. So if you add one more point, how many new edges do you actually have? So this is where the 6 comes in and where we have the 12. And this proves the lemma and proves then therefore also the main result. Remember the harmonic numbers, where we can actually bound the sum of the 1 minus r, so we let r goes from 1 over n. This gives actually the logarithm. So we have the n log n proof of the lemma. Okay, so this is a complicated lecture, but in some sense quite easy to summarize. So the Delaunay triangulations can be constructed in n log n time on average, so which means that we have to randomize our input. This is already the third time that we do a cost analysis. So the textbook continues with providing a unified framework for analyzing randomized algorithms. So in some sense, if the I'm certain that this lecture went too fast, so it could be a very interesting theoretical study, and which would count also as a final project to do actually that analysis, to actually give an overview of the ideas that we have used in the other randomized algorithms that we have considered already in this course, the trapezoidal maps and the incremental linear programming. Okay, so there are the usual activities that are recommended. We essentially spent only 3 lectures, only one chapter on triangulations, although it's deeply connected with Voronoi diagrams. One could spend an entire graduate course on triangulations, and I'm finishing with this reference to a truly beautiful book um, that is listed here entirely on triangulations.